Good day, sir. My name is Marijo Monida. I'm from BSME 2P. Today, we're going to discuss a problem of a thermocouple at equilibrium with ambient air at 10 degrees Celsius. Plug into a warm water bath at time equal to 0. The warm water acts as an infinite heat source of 20 degrees Celsius since its mass is many times that of the thermocouple. Calculate the response curve of the thermocouple. Data. Time constant of the thermocouple is 0.4 minutes subdivided 1, where Cp is thermal capacity of thermocouple, U is the heat transfer coefficient of thermocouple, A is the heat transfer area of a thermocouple, and time and the temperature of the thermocouple, temperature of water, and the temperature of ambient air. So we're going to use the Ron's-Cotta methods. Theta equals temperature of water minus temperature of thermocouple over temperature of water minus temperature of the ambient air. So N equals the thermal capacity of thermocouple over heat transfer coefficient of thermocouple times area transfer area of the thermocouple equals the time constant of the thermocouple. So the time equals total time equals T over 10. So the governing differential equations is Newton's law of heating, and Newton's law of cooling is the thermal capacity of the thermocouple and the temperature with respect equals to temperature with respect to time equals heat transfer coefficient of thermocouple over times heat transfer area of a thermocouple times close parenthesis equals close parenthesis temperature of the water minus temperature of the thermocouple close parenthesis. So the temperature where temperature is 10 degrees Celsius and time equals 0. If the response curve is calculated for 0 is lesser than t and t is lesser than or equal to 10 minutes, then the theta is with respect to t equals negative 25 theta. Theta equals 1 at time equals 0. The analytical solution is this, which is 0 is lesser than or equal to t total and t is lesser than or equal to 1. Now we will solve the differential equation using the second order Ron's-Cotta method. So this is the u equals 1 and these were fi equals negative 25 ui and this and using Ron's-Cotta method, and this is the formula. So shows that this table shows that generated results. Notice that n equals 20. The second order Ron's-Cotta method shows large discrepancies when compared with the analytical solution. Since lambda equals negative 25, the maximum stable step size for this method is h equals 0.08, and for n equals 20 is very close to this maximum. For the Ron's-Cotta method, The maximum stable step size is h equals 0.1112 and h never approaches this limit. One can also see that the Ron's-Cotagel method produces a more accurate solution than the second order method, which is as expected since it is a fourth order accurate. To further this point, when we were compare the first for a given n, the accuracy increases with the order of the method as one would expect. Since Taron's Cutagel method, Arcadia requires 4 function evaluation per step while the Euler's method requires only 1, which is computationally more efficient. One can answer this question by comparing. So therefore, shown that for this problem, although more functions evaluations per step are required by the higher order accurate formulas, they are computationally more efficient when trying to meet a specific error tolerance. This result cannot be generalized to include. Physically, all the results have significance since theta equals temperature water minus temperature of the thermocouple times over temperature of water time minus temperature of the ambient air initially. So T equals the temperature of thermocouple equals temperature of the water, and the theta equals 1. When the thermocouple is plugged into the water, the temperature will begin to rise and the temperature will approach to temperature water. That is, theta will go to 0. So far, we have always illustrated the numerical methods with the problems that have analytical solution so that the errors are easily recognizable. In a practical problem, analytical solution will not be known, so no comparisons can be made to find the errors occurring during computation. Alternative strategies must be constructed estimating the error. So therefore, for the Ron's-Cotta formulas, using the one-step to half-step procedure can be very expensive since the cost of the computation increases with the number of function evaluation. And we have presented methods that increases the order accuracy, but their stability limitations remain severe. And that's all for my discussion, and thank you. So